Hi folks, welcome to Chapter 4. This is Simple Linear Regression. All right, so in our applied course, we're constantly attempting to discover and understand the relationship between variables. For example, we might want to know about the relationship between rainfall and crop yield for farmers. Number two, we might want to know about the relationship between COVID stay-at-home orders and changes in consumer spending. Number three, we might want to know about variables in general that impact a company's yearly profit. We're trying to understand these relationships. So collecting data, we attempt to estimate a statistical relationship between one or more variables, attempting to understand the world. That's our job here in applied econometrics. Now in this lecture, we'll focus on simple linear regression where there was only one regressor. So just a little x in our equation. Once we estimate the relationship, we can use this information then in multiple ways. Very valuable. Number one, we can identify the causal effect of one variable on another. So for example, if and how height might impact your salary. You might think they're unrelated, but they're probably related to some degree. Number two, we can think about how to predict the value of a dependent variable given initial values of other variables. For example, suppose you're an analyst for a car dealership and you're trying to predict the number of daily cars sold for a given number of salespeople. Or it's your job to potentially make the schedule. Now you collect historical sales data when there's 1, 3, and 4 salespeople working, and you estimate a relationship between these variables. Now you can use this estimated relationship to predict the number of daily cars sold. On average, if instead of having 1, 3, or 4, if instead you only have 2 salespeople come to work. So we'll explore the methodology and applications for simple linear regression in this chapter. Now this chapter will be to some degree review. Some of you saw it last quarter, some of you saw it a few quarters ago, but it's good review to progress well in the course. All right, so what's our agenda for this chapter? Number one, we're going to talk about the population linear regression model. This is essentially the true relationship between variables if we knew everything about all. Okay, but the reality is we don't know all the data. We don't have access to all that data, and sometimes data is misrepresented or collected improperly. So what we need to do is sometimes understand the world by collecting sample data. So we're going to derive and utilize what's called an ordinary least squares estimator, and then we're going to utilize that to define the sample regression line, right? So we can understand the relationship between two variables. Once we've done that, we'll talk about measures of fit. Right, it's one thing to actually estimate relationships. It's another thing to say how strong this model is in predicting your dependent variable. Just because you've ran some fancy regression doesn't necessarily mean that the results are valuable or they explain the world to a sufficient degree. So we'll talk about measures of fit, and then we'll talk about important assumptions we make for our sample estimator to be identified as causal. Okay, we'll talk about that soon enough. And then we'll also talk about the sampling distribution for this OLS, or ordinary least squares estimator. Right, this will be particularly helpful, this fifth step, for defining confidence intervals and hypothesis tests in coming chapters. So starting off, let's talk about the population regression line and identify what we're trying to achieve with this type of analysis. All right, so right here, what we have is an expectation. Expected value of y given xi. We're trying to understand the value of y. We're trying to anticipate it given some other variables. So y are our dependent variables, and xi we're going to identify as our independent variables, or things we're actually controlling for. And the relationship between our y's and our x's will be given by this population regression line, where we have beta naught. This will be our y-intercept. We'll have beta 1 times xi. So xi is our independent variable, and beta 1 will be the impact of that variable on our dependent variable y. And then we'll have some error term that we'll talk about soon enough. Now, one of the most important points of this relationship is trying to identify how directly this variable x impacts y. What is the causal effect? Here, we can interpret this as a regression slope. Okay, because what it's trying to do is it's trying to identify if x changes by 1 unit, either upwards or downwards, what is the net impact on our dependent variable, y? Okay, so formally, we can identify beta 1 as the difference in the expected value of y for two values of x that differ by 1 unit. So if x goes from, let's say, 2 to 3, let's say x represents rainfall and we're measuring it in inches, then we might want to identify what is the impact of 1 additional inch in rainfall on crop yield. Right? So beta 1 would give us that information as to the causal impact. So what are the particular benefits? What are the uses of regression equations? Well, we have two that are of particular importance. Number one, we're trying to identify the causal inference. We're trying to understand how one variable is directly impacting another. And that's by looking at what this beta 1 coefficient is. If there is a positive relationship, then this will be a positive variable. If there's a negative relationship, then there'll be a minus sign in front of the beta 1 coefficient. We're trying to understand it. So it's both the sign of beta 1 that's important, but also the magnitude that tells us information about how these variables are related in the real world. Now, number two, how else are these regression equations useful? With prediction. Quite frequently, we're looking at data of the world and we're trying to understand and anticipate the future. And we might have information, again, on certain characteristics of x and y, but we want to see what happens to y if x is a little bit bigger or x is a little bit smaller. We can use an estimated relationship between these two variables to predict these causal effects. Now, again, in particular, this is very helpful for an observation that is not in the data sets. So what I talked about in the intro slide, whereas we're looking at car salespeople and how they have an impact on sales. Let's say we've had one person on the schedule, 3 and 4. We never had just 2, but we want to estimate how much in daily sales might we anticipate or might we predict if we have just 2 people. So using a regression relationship, we can identify what the y variable would be for observations that are not in the data sets. So 2 salespeople. Now, this type of information is powerful. It's powerful. It's powerful for both policymakers at the government level or at the decision level for individuals or for firms. Right? Everybody benefits from estimating relationships between multiple variables. Now, the reality is the population regression equation that we saw in the prior slide with the beta naught and the fancy beta 1, those Greek letters, those are population variables. And that's if we know everything about the world and we have perfect information. The reality is we don't. Information is sometimes difficult to collect or it's imperfect when it's actually measured. The reality is we'll never know the population coefficients with certainty. So what we do is the next best thing. We estimate them. All right, so we look at, let's say, a graph. And here I've drawn just a simple diagram that's looking at the relationship between x and y. And for estimation, we have some issues that we need to discuss. Okay, so we see with these data points up here, information that we collected, that there pretty much is a positive relationship. As x gets bigger, so does y. But the question, though, is how should we draw a line through the data to estimate the population slope? Because the reality is, I can draw it like this. I can draw it slightly like this. I can draw it like this. And each one of these lines is positively sloped, but they have different slopes. And if the slope identifies the causal impact of the x variable on our dependent variable y, then we want to try to estimate the slope as perfectly as possible. All right, so what's the best way? We can't just draw lines because everybody here will draw a different line. Instead, we're going to use OLS, ordinary least squares. So in the coming slides, we'll talk about the advantages and disadvantages of this method, and we'll talk about the necessary assumptions. Now, once we've estimated the slope parameter and different coefficients, then we want to put our results through rigorous testing to identify if we have significant results. Or with the sample data, is it possible that our output doesn't actually hold any merit? So what we will do, and you've seen this in prior probability and statistics classes, is we will use hypothesis testing to determine whether or not the slope coefficient that we would have estimated via this type of regression is statistically significant, or just like a random variable, is it arbitrarily a positive or negative number, and more realistically, 0. We're going to set a null hypothesis that these coefficients are 0, and we're going to try, hopefully, to reject our null hypothesis and in favor of our alternative hypothesis that these variables are indeed significant. They're significantly positive or they're significantly negative. They actually have a non-zero impact. We'll also talk about how to utilize confidence intervals. So we can talk about the slope, and these two tools right here will be gone over at length in the next chapter. All right, but before we can actually estimate confidence intervals and we can utilize hypothesis testing, we first have to estimate our coefficients and look at our standard deviations and collect this information before we can actually run rigorous analysis. Now, looking at a particular example, let's look at the population regression line between test scores, average test scores, and the student-teacher ratio. So we know in general, at least in theory, we know that more students in the classroom are more taxing on a teacher's ability to teach, and that might decrease test scores. Now, as you decrease the number of students in a classroom, that leaves a teacher with more time to work on with each student individually. That might increase test scores. So we might see that there's an inverse relationship between these two variables. That's our hypothesis. We need to collect sample data to try to estimate this hypothesis and see if it's actually correct. All right, so our dependent variable then is test score, right here. And our independent variable then, let me change this to red, will be the student-teacher ratio. And right here, beta 1 then is the slope of the population regression line. And it tells us, at least in theory, what is the impact of the student-teacher ratio going up by 1 or down by 1. How does that impact test scores on average? All right, so our objective, it's important to keep this in mind, is we're trying to identify the impact of student-teacher ratios, which you can just say is class size, on average test scores. Okay? What are policymakers going to do with this? Well, sometimes they have the money to reduce the size of classrooms by hiring more teachers and spreading out the students. If they see this as worthy, they might invest in additional teachers so that they can increase their average test scores across their classrooms so that they can get more grants from, let's say, the state or the federal government. Right? But sometimes these teachers and these schools acknowledge that while it is true that less students in the classroom will increase the test scores, maybe it's not justified to spend so much by hiring 10 more teachers. Right? So the way to make these decision-based observations is to collect data and try to first identify this relationship between class size and test scores. Now, in our population regression equation, we have beta naught is our intercept and beta 1 is our slope. These are population parameters. And population says this is the true impact of these two variables on test scores. So beta 1 is the true impact of the student-teacher ratio. The true impact, if we knew everything about every single class in the country and the world, if we had all that information perfectly and nothing was measured improperly or with measurement error, then we would know what beta 1 is. Okay? Beta naught would be the average impact from a classroom that actually had 0 student-teacher ratio. Right? So it doesn't always make sense what the y-intercept actually means in economic terms. But the reality is here, population parameters, they're not achievable. They're not accessible. They don't exist. It's just hypothetical. Right? So we would like to know the population value of beta 1, but we'll never know this. So what do we do instead? We estimate it using data, the next best thing. So taking some time to look at the actual notation of our population linear regression, let's break this down and talk about this so that we have a solid foundation moving forward in the course. All right, so you have our dependent variable y. Got it. We have our independent variable, or our regressor, x. And one thing that is important to talk about is we have a little subscript I on both of these. All right, so the reality is we're collecting data. We're collecting the height and income for person 1. We're collecting the height and income for person 2. For person 3, we're collecting them for I different people. All right, so we have n observations, and we're going to collect both data pieces for these individuals. So I happens to be the individual, or the classroom, or the nation, or the company. It's just a collective unit. Now beta naught right here is our intercept. Got it. We have beta 1 right here, we already said, is our slope. And one thing that we don't want to ignore, because it is quite important, is our error term, UI. Now, what's particularly important is we're trying to estimate the relationship between two different variables. How does our xi variable impact our yi variable? Okay, there is an impact, but really a regression is trying to understand what variables and the degree to which these variables impact it going up or down. So again, if our dependent variable happens to be test scores, it is true, I'm sure, that student-teacher ratio will impact test scores, but there probably are other factors that might influence test scores. So what does UI actually represent? Our error term consists of two things. Number one, it consists of all of the emitted factors and variables other than our controlled for variable x that actually influence y. Right? What else actually impacts the test score, the average test score in a classroom? It might have something to do with income level for the city. It might have to do with the composition of the class. Is it made up of all English speakers? Is it some English speakers? What's the composition? It has to do with student level characteristics, right? That's probably going to impact test scores. There are a lot of other things that we're not controlling for that are just bundled up into the error term. So our error term per individual I is going to include these emitted factors, number one. And then number two, our error term will also consist of measurement error of y. So when we actually are collecting information on test scores, and we're trying to identify the impact of student-teacher ratio on test scores, the reality is, sometimes test scores are not collected perfectly. We like to think that computers and teachers, we are impervious to mistakes, but the reality is that's not true. So there happens to be some measurement error that's included within that regression error term, UI. Right, so these are the individual components of our population linear regression. Let's go ahead and look at 7 hypothetical sample data points, and let's look at the population linear regression, which is going to be this blue line right here. Now we know it's our population linear regression because we actually have Greek letters right here for the coefficients. We have beta naught and we have beta 1. A little bit later, you'll see when we estimate these coefficients, sometimes we use B1 and B0, right, to identify that those are estimates. Okay. Now, what can we say qualitatively between the relationship of student-teacher ratio, x, and our test scores, y? Well, looking at the population linear regression, it does happen to be downward sloping, which means that our beta 1 coefficient is going to be negative. And what does this suggest? This suggests that smaller student-teacher ratios are going to increase test scores, right? So there's the inverse relationship, or alternatively, higher student-teacher ratios are going to lower test scores, at least on average. It's not always true, but this is on average. Now, what else can we extract qualitatively from this information? Well, we see something about the slope. We are also interested in usually the intercept, beta naught. Beta naught is going to be the intercept right here. Okay, but what does that actually represent? That would represent the average test score in a classroom that has a student-teacher ratio of, well, here this says 10, but let's imagine that it goes all the way back to 0. What does that even mean? There are no students to that one teacher. How can there be any test scores? What's important here is while our regression analysis will estimate both the slope and the intercept, sometimes it's true that the y-intercept does not always have a real-world meaning or interpretation. Okay, here, a student-teacher ratio of 0 doesn't mean anything. It's an empty classroom, and somehow there's still an average test score. Doesn't make sense. All right, so important to always know contextually what these variables mean. All right, so lastly, the thing we want to kind of point out are the regression error terms. This is U1, this is U2. So looking at U1, let's say this blue line, this blue downward sloping line is the true population linear regression. Well, our sample data points, they don't necessarily fall exactly on it because we don't have a perfect relationship. Let's see U1 though. So we see that the error term can sometimes be positive or it can be negative. So right here, our data point right here is higher than our regression. So we have that U1 is positive. And down here, we have that U2 is smaller than our population linear regression, which means that U2, our error term, is going to be negative or less than 0. Now, what causes these deviations from the actual population linear regression line? I mean, it could be a few things. It could be omitted variable bias, which we talked about in the prior slide. It could also just be a simple measurement error. Which one is it? We don't exactly know with this dearth of information. Again, our overall main objective is to understand this relationship between these two variables. So in theory, we can modify education policies or we can predict scores to reallocate scarce resources for educational funds. Okay, but the issue is here, we cannot actually identify ever these population parameters, beta naught and beta 1. Okay, we don't know everything about the universe. We only know a subset of that. Nor do we have enough money to actually collect every piece of information. So what do? We need to estimate these population parameters. All right, so how exactly do we estimate both our population intercept and our population slope from the data? Well, let's say you have a little bit more data. You're trying to fit a line. We're trying to understand this true relationship. We can fit a line that looks like this, or we can fit a line that looks somewhat like this. We could fit a line that looks like this. And you and I might agree that each one of those three look possible. And you might say the first one is the best. I might say the second one is the best. But again, we're human. We, via the eyeball test, can't actually structurally say which one's the best one. Okay, we need statistical procedures to actually identify that best fit line. So to the rescue, we're going to utilize this OLS estimator. We're going to choose both B naught and B1, which again are estimates for beta naught and beta 1. So our betas happen to be population parameters. And we have B naught and B1 being their counterparts. These are going to be estimated regression parameters. Okay, so our goal then is, since we can't ever know both beta naught and B1 and beta 1, we don't have infinite knowledge of the world. Instead, we're going to estimate these by using B naught and B1 to minimize the following equation. So we're looking right here. So let's break this down. What do we know about yi? Yi are our true observations for the dependent variable. Xi is the true observation for the independent variable, while B naught and B1 are estimates, okay, for our population parameters. So what we're trying to do is we're trying to find what is the difference between our true observation of yi and our estimated value of yi. Because we said that yi, the true population regression equation, is beta naught plus beta 1 xi. If we instead substitute these betas with b naught and b1 xi, then what we're doing is we're estimating our yi, because we're using estimates of our population parameters. So our yi, again, is our true observation of y, and then beta naught plus beta 1 times xi is our estimated value of yi. And we're trying to figure out how can we minimize the true value of yi that was observed and our estimated value that is predicted using our regression equation. So what we do then is for every single, so it's getting a little messy, but for every single, let's go with black, for every single observation I, all the way to the nth variable, what we're going to do is we're going to take that difference and we're going to square it and then we're going to find the summation right here. All right, so cleaning this up, let's go with yellow. The OLS estimator then is going to minimize, let me highlight this first, it's going to minimize the square difference between the actual and predicted values of yi. Okay, so if we can minimize the errors, if we can minimize the mistakes choosing B0 and B1 predictably, then this will be the quote-unquote best estimator of these two parameters. So in simple terms, the OLS estimator of both beta0, or for both beta0 and beta1, is going to minimize the sum of our squared, let's say, mistakes, right? Yi minus, let's write this down, yi minus yi hat. If there's a difference, it's because we made a mistake estimating this yi hat, okay? We're trying to minimize the squared difference of these mistakes by choosing the OLS estimator. That's the goal. Now to estimate our population parameters, both our beta0 and our beta1, change it back to red, we can use the below equations. So we can say that either beta1 hat, or sometimes the book says B1, is given by the above equation, and the second one is beta0 hat. The hat suggests that we're estimating something. Sometimes you'll see this also written as B0, so B0. All right, so what do we have? We can take our sample data and we can apply these following equations. You may have actually utilized these equations when you were in probability and statistics. They are a little bit of a nuisance to calculate by hand, but what's lovely about applied econometrics is you will not have to calculate these by hand. You'll actually have regression software that will do it for us. All right, but if you needed to do it by hand because the computers of the world are breaking down, what this says right here is we're going to, for each individual observation, we're going to take that observation's x and subtract from it the mean of x, that's x bar, and we're going to multiply that by the observation y and subtract y bar from that, the average of y, and then we're going to divide by xi minus x bar squared. Okay, so effectively, what we have is in the numerator, we have sxy, which sometimes is called the covariance of x and y, and that's going to be divided by, well, this equation right here should look a little bit familiar. This is the variance of x. All right, so technically, if you have sample data, if you're running this in Excel, then you can run this by hand, and then we can take the sum of these up here for all I and the sum of these down here, and we divide the two. That will be our estimate for our slope parameter, beta1. Now, once you have beta1, the estimate, then we can plug it into this equation down below to find beta0. And that simply says take the average of y and subtract from it our estimate for beta1 times the average for x. That'll give us our estimate for our intercept parameter. Now, once you have our OLS estimators for both beta1 and beta0, then we can utilize that information to run some predictions. Right? We said sometimes you want to know what is our dependent variable going to be for different out of sample values, for our independent variable x. All right, so we can take our beta0 hat and we can add to it our beta1 hat times that x, and we can find the predicted value of y. Now, we talked about our error term, our regression error term in prior slides. Here, our error term is going to be estimated, okay? So we're going to have our observational level of y, that's yi, and we're going to subtract from it the estimated value of y. Now you might ask, why are we estimating the value of y? Well, what we're trying to do with our OLS estimator is we're trying to minimize our mistakes. So yi is the real observation, and yi hat is the estimated observation. So the reality is, if we can minimize the distance between yi and yi hat, if we can minimize the mistake in our regression, then we can minimize those error terms. And if we can minimize our error terms, well, qualitatively, that's a great thing. Okay, that's what the OLS estimator is trying to achieve. Now, just for some notation and for some definitions, we call this estimated error term, when we're actually estimating our yi, we call these residuals of the regression. So a residual is the difference in the actual observation of y with its estimated version. That is a residual of the regression. All right, so go ahead and looking at an application and trying to interpret actual empirical results. Let's take those prior equations for both the slope parameter and the intercept parameter and try to estimate this regression. All right, so we have software and it's going to spit out the following equation. Okay, so we have right here that the estimated intercept is 698.9, and we have the estimated slope is going to be negative 2.28. Right, so thinking about interpretation then, this suggests that if we increase the student-teacher ratio by, let's say, 1 student, what this will do is this will decrease, since we have a negative sign, this will decrease test scores on average by 2.28 points. So in the context of this model, this says that adding 1 more student will hurt average scores, not by a lot, but still by an important amount. Here, 2.28 points. Now interpreting the estimated intercept, right, this is a world where, and again, going back all the way, let's see if this keeps kicking up. This stops at 10, so it's a little bit nonsensical, but let's say it went all the way back to 0, if they graphed that properly. This would say that when the student-teacher ratio was 0, so there's 0 students per teacher, then the average score would be 698.9. All right, so sometimes these estimated intercepts, or these intercepts in general, have no real-world interpretation. All right, so let's go ahead and take the estimated regression, which we have right here, this equation, and let's use it to look at predicted values and estimated residuals, or errors. All right, so let's select a particular district. So we're looking at districts all over the state of California, let's say the West Coast, and maybe all of the United States. And let's look at one Antelope, California, which case we found that the student-teacher ratio on average was 19.33, and the average test score was 657.8. Okay. So that's real observational data. This is real. And we know that that one data point does not dictate the estimated regression line. It's all of the data points together trying to minimize our error terms, our squared error terms. So let's see then from this observational data, what does our regression actually predict as far as our dependent variable? So we have y hat trying to estimate what our y variable would be here. It would be test scores. We take our intercept and we subtract negative 2.28 times our observational x value, 19.33, and this returns a value of 654.8. Now we know the true value is 657.8, which means this underestimated it. Okay, it's an error. So let's quantify that error. So the estimated residual then is the true value, or yi, minus the estimated value, yi hat. And this happens to be 3. So right here, our actual observation then is going to be 3 units higher than our predicted value, or we can say simultaneously that our predicted value is 3 units below. All right, it's a mistake. And it's not a bad thing, right? Because we're trying to take all of this data right here in this diagram and find the one perfect line that's going to minimize these squared error terms. Not an easy task. Now this is an applied class, and what would an applied class be without talking about actual regression analysis and output? So here, let's look at the same exact data and hypothetically put it into our Stata program, and let's try to understand the output. All right, so we're going to look at Stata output. And so what we're going to do here is we're going to go, and I think you can do this actually from the data in the textbook as well. You're going to go into Stata, you're going to import your data. We can talk about that in section or in office hours, but you're going to regress. This right here is going to be your y variable, the first variable you say, test score. And then str is how they coded their independent variable. That's their x. And we're going to put comma robust. Sometimes you'll also see comma r. So something interesting about Stata is it doesn't mind if you abbreviate or if you shorten the length of a word if it's not a variable name. So sometimes researchers get a little lazy. Instead of typing regress over and over, I know what I do is I put reg. If I put reg, Stata knows implicitly that I'm trying to do regression. And if you put comma r, that's the same exact thing as saying comma robust. All right, but you don't have to take shortcuts. There's no need for that. All right, so when we do that, what it's going to do is it's going to use OLS, the techniques that we talked about in the prior slides, to estimate these coefficients. One for the slope, that beta 1, and then 1 for the intercept, beta naught. And what we have right here is the coefficients that it just estimated. Okay, so whereas before we found our slope to be negative 2.28, this says the same thing, right? Negative 2.279808, rounding to negative 2.28. Perfect. And then we estimated in our prior slide that the intercept was 698.9, and we see the true estimate is, well, effectively the same thing with a few 3s at the end. Okay, there is a lot more output right here, and it all is important, but we'll discuss those a little bit later in the chapter and in the next chapter as well. Right, so two ways, actually there's actually a few different ways to calculate the coefficients for simple linear regression when you have just one regressor or one independent variable. Number one, you can actually plot this data in Excel, right click and add a trend line. That's interesting, and you can have it tell you the equation. It'll give you the same exact information and answer. Number two, you can go the more laborious way in Excel, and you can actually use the equations for beta naught and beta 1, right, and then get the same exact answers. Or three, you can go the easier route, the more applied routes, and utilize software to our advantage, which is a lot more efficient and a lot less prone to mistakes. Either way, all three methods, doesn't matter which one you utilize, should get you the same exact answer. Now, in these lecture videos, I'm going to take a lot of time to not only talk about the theory a little bit, but a lot of application, right? So you just saw in the prior slides looking at some Stata output, so looking at actual statistical software. We're also going to take time to look at examples from the end of the chapter, right? Because exams and labs are going to be a combination of problem solving and lab work. So I would like you to get used to and get some exposure to both of these types of problems. So we'll do a lot of these types of problems within our lecture. All right, specifically here, we're going to look at exercise 4.1. And here we have that a researcher using data on class size, CS, and on average test scores, this sounds familiar, from 100 third grade classes is going to estimate the following regression. So again, we're trying to estimate our dependent variable test score. We're going to have a independent variable of class size, very similar to student-teacher ratio, and we're going to estimate the relationship between these two variables. We're estimating that. We find then that the slope is negative 5.82 and the intercept is 520.4. We'll talk about this other information a little bit later. All right, A says a classroom has 22 students. All right, sounds good. What is the regression's prediction for that classroom's average test scores? All right, so we took 100 data samples, okay, these observations, and now we want to utilize that estimated regression to predict or forecast or identify what do we anticipate being the average test score if there's only 22 students. All right, so what are we going to do? We're going to have that our y hat is going to be equal to, well, 520.4. We estimated that to be the intercept, minus 5.82. And we're going to multiply that by, well, I'm saying hypothetically there are 22 students. Multiply that by 22. Now with your handy dandy calculator, this is going to equate to 392.36. All right, so observationally, from our estimated regression, this says that if there happen to be 22 students in this class, this is not saying that definitively the average score is going to be 392 and change, but on average, the average score will be 392. Now you might say, why is that important? Well, if you are, in the administrative office and you're trying to maintain a certain type of standard across your classrooms so that your school can get funding from the state or from the federal government, then you need to maintain some form of average test scores, right? So you then, as the administrator for the school, might want to anticipate what would the average score be with classrooms of size 22. So this information then, in theory, even though it's not definitely what's going to happen, okay, but it's our estimated results on average, this can be used in the decision-making process to allocate scarce resources. Right, so in theory, we are bridging the divide between quantitative methods and economic analysis, hence econometrics. All right, let's go ahead and look at part B for exercise 4.1. Right, so we still have the same information right here. And this says last year, a classroom had 19 students, and this year it has 23 students. Okay. What is the regression's prediction for the change in the classroom average test scores? So there are a few different ways you can do this. You can technically calculate what is the estimated Y when, let's see, class size is equal to 19, and you can compare that to the estimated Y when the class size is equal to 23, and you can subtract the two, seeing what the net difference is. Or you can realize that in both of these equations, star and let's say star star, they share the same exact unchanging intercept. So those will go away. All right, so because those will be eliminated, what we can do then is just compare how is the rest of it right here changing for different values of the class size. So what we can do then is we can do, so at 23, since that's the bigger one, we have negative 5.82 times, let's see, 23. And we're going to subtract from that negative 5.82 times 19. And what you're going to get right here is you're going to have negative 23.28. So this suggests empirically that if we increase our class size from 19 students to 23 students, so adding 4 more students on average, this will decrease average test scores by upwards of 23 points. That's one way to do it. Another way to do it is say the change then in test score, where this little triangle mirror here means something's changing in mathematical notation. Well, we know the change in test score is going to be equal to, well, this right here does not change, so we'll leave that alone. We have a slope of negative 5.82, and we're going to multiply that by the change in class size. The class size technically changed by 4, so if we plug in a 4 right here, we'll have 4 times negative 5.82, which again will be equal to negative 23.28. All right, so a few different ways to think about this. They are all more than sufficient. All right, last but not least, in part C, this says the sample average class size across 100 classrooms is 21.4. Right, it's the sample average class size. What is the sample average of the test scores across the 100 classrooms? All right, so this says, hint, review the formulas for the OLS estimators. So from those prior formulas, we had that y bar, so the average y is equal to b naught, which is the estimate for beta naught, plus beta 1, or b1, excuse me, times x bar, so the average x's. So what do we have? We have that b naught is equal to 520.4. We have that b1 is equal to the negative 5.82. And this says that the average sample class size, so our x, is going to be 21.4. We're going to plug this in right there. So when you plug in those 3 values right there, what you're going to get is 395, if I didn't mess this up, 0.85. Right, so what is the value in that? We have right now not necessarily the estimated test score for one particular class using our regression. This might be instead the average test score for all classes in a school, okay, that have an average number of students. So overall, just a different type and level of analysis that we can think about with this particular regression output. Now let's go ahead and switch gears now. Right, it's one thing to measure the statistical impact of one variable on another, but the reality is when we estimate these, we are using sample data to explain a real-world phenomenon. So a question we have to ask ourselves is how well does this estimated relationship actually describe and fit the data? Right, so we're going to look at two different measures of fit, and we're going to try to ascertain what they tell us about the model. Now, number one, let's look at R squared. Or you probably have come across this in, again, your probability and statistics classes, but this measures statistically the fraction of the variance of y that is explained by x. So to what degree x is going to help predict y. That'll help give us some idea as to the fit of our model. And what's important about this is technically this is a number that is between 0 and 1. 0 means it doesn't fit the data at all, or 1 means it predicts y perfectly, usually some fraction in between. This is unitless. All right, and again, it ranges between 0, no fit, and 1, perfect fit. Now we have standard deviations that we will measure for our estimators, but realize beyond those estimators, we're also looking at the overall regression as a whole. So number two here, what we look at is something called the standard error of the regression. And in the output, sometimes in the state output or the software output, you'll see it abbreviated as SER. And this measures the magnitude of a typical regression residual. Okay, so this estimated UI. Recall that UI hat is equal to YI, the true observation minus YI hat. And this gives us information about the average residual, or that average error term. Now, this one happens to be in the same units as y. Y is our dependent variable, so however that is actually measured, be it in points, be it in pounds, the standard error of the regression will be in the same exact units. All right, let's break these down. We're not going to get too involved. We're not going to talk about the theory behind this or the abstract calculations, because this is an applied class. But let's look at this in general, and let's understand the working components. So again, R squared is the fraction of the sample variance of y that is explained by the regression. So we're trying to understand to what degree our predictor variables, our x's, can predict or anticipate the fluctuations in our dependent variable, y. So looking at the formal definition of R squared, this one right here, we have in the numerator, we're going to take the sum of the predicted value of y, so yi hat, and we're going to subtract from that all of the average, so the average of the predicted values of y. We're going to square that and we'll sum those all up. And then in the denominator, we're going to take the actual observed level of y. This is our yi. And we're going to subtract from that our y, or average of our y, so y bar. And then we'll square that. So effectively what we have is in the bottom, we're looking at true values of y, right? Actual observed values of y, and how each individual y differs from the mean, y bar. Okay, so trying to find that little variance right there. And then in the numerator, circle this in green, what we're doing is we're looking at not actual observations, we're looking at estimated values of our dependent variable. And we're going to subtract each one of those estimated predicted values by the mean. So y bar hat, it's a mouthful. All right, so we're looking at one variance over another. Now, anytime we have that r squared is equal to 0, or it's really, really small, that must mean that this explained sum of squares, this is from the regression estimation, when that itself is 0. Okay, anytime r squared is closer to 1, I mean, equal to 1 is most likely not going to happen, then that must mean that the explained sum of squares in the numerator exactly equals the total sum of squares, which is in the denominator. These are actual observations and their variances. All right, turning the page to the standard error of the regression, again, think about residuals, how much we are getting things wrong by estimating our dependent variable compared to its actual observation, y. All right, so in general, we have that the standard error of the residual, or excuse me, of the regression, SER, is going to measure the magnitude of a typical regression residual. So the average mistake that we're making by fitting and estimating this regression line. Now, this is sort of a complicated formula. And again, like all applied topics we'll talk about, thankfully, Stata and regression software does a really good job of just conveniently calculating it for us. But it's important to know where it comes from so that we can interpret it properly. All right, so what we have functionally is we're going to take the squared difference of the estimated residual and subtract that from the average of the estimated residuals. We'll take that difference, we'll square it, and then we'll sum them, and we'll multiply that by 1 over n minus 2. And so really quick, sometimes you see estimators that are multiplied by 1 over n minus 1 or n minus 2 because they're trying to find some type of average. But instead of just there being an n in the denominator, we do n minus 1 or n minus 2 to correct for biased regressors. Now, when we divide by n minus 2, what we're doing is we're controlling for degrees of freedom. We literally took data points and we estimated 2 functional parameters. So we need to correct for that downward bias, and we need to correct it right here by dividing by n minus 2. All right, same thing in each of these. All right, so we have this first functional form right here. Later, we'll see one of our OLS assumptions is that the estimated residuals on average are equal to 0. So that's what this line right here says. So we can drop off this right-hand term right here. And we're left with, let's clean this up. Left with this equation right here. So this says if we want to calculate by hand, if we really wanted to, the standard error of the regression, we would square each of the estimated residuals. We would then sum that up, multiply by 1 over n minus 2. That would give us the variance, and then we would take the square root to find that standard error. Sometimes, depending on the software that you're using, they actually might return a value called SSR, which is the sum of the squared residuals. That's exactly what this number is right there. And then they just divide that by n minus 2. So the output that you see in Stata is a lot of pieces, and sometimes we put together those pieces to interpret it for different analytics of our model. Now, Stata output also reports something called the root mean squared error, which actually is very, very, very much related to the standard error of the regression. But instead of dividing by n minus 2, the root mean squared error actually divides only by n. Okay, so they are related. So the root mean squared error is equal to the square root of 1 over n, the sum of the ui squareds. So the ui, estimated ui's squared, and it's going to divide by n instead of n minus 2. And they get away with this because in large sample observations, dividing by n or n minus 2 actually doesn't make that big of a difference. Okay? It's going to be still a small number that you're multiplying by. So the softwares, in their infinite wisdom, they report the root mean squared error as 1 over n times the squared sum of those estimated residuals. And this information is just one more tidbit to analyze when we're thinking about the fit of our model. All right, so going back to our regular data, we have student-teacher ratio on the horizontal axis. Got it. We have our test score on the vertical axis. We've estimated our regression. Okay. We've already talked about the estimated intercept and the slope right here. Now let's look at the other output. We have r squared is equal to 0.05, and the standard error of the residuals, or the regression, is 18.6. So look at r squared first. What does this mean? Technically, this means that our independent variable, which is the student-teacher ratio, only explains 5% of the variance in our dependent variable. So it doesn't actually explain much of why the dependent variable test scores increases and decreases. It's a small component of it. All right, so a small fraction of the variance in test scores. Now, does this make sense? Does it make sense that student-teacher ratios, they are potentially important, but they don't actually explain the totality of why test scores go up and go down? I'll say yes, because the reality is there are so many things that actually will derive and impact how test scores go up and down. You think that student-teacher ratios are the main driver? I'm going to say it's important, but it's probably not the complete story. And here, this suggests that it's only about 5% of the story. Now, thinking in another way, does that mean that the student-teacher ratio is unimportant in a policy sense? Not at all. This is but one important variable. And right now, we're just looking at a very simple linear regression, but we're only controlling for that one independent regressor variable. We cannot necessarily say that it's unimportant. It just doesn't have a large influence on the overall model. Okay, but maybe no variable has a staggeringly high magnitude of an impact on the test scores. Maybe there's 20 variables and they all collectively impact test scores. I guess we'll see. So let's say this for a second. Because this is all thinking about this in practical applied terms, sometimes researchers and students, when they're running empirical original analyses, they equate a low R squared as something that's potentially bad. And we really shouldn't think about it like that, because really a low R squared just means that there's many other variables that influence test scores that we can potentially control for. So right now, if we only control for test scores, we don't understand everything about how test scores fluctuate. It just leaves us more opportunity to explore the world a little bit more. Now we see the standard error of the regression is equal to 18.6, which tells us something about the average distance of the residuals from the estimated regression. So this is relatively large. So looking at it visually, so from here to here, and here to here, and here to here, and here to here. If you calculate all these residuals, this gives us an indicator of that average spread. Now, if you're trying to predict, let's say, the test score by using class sizes, because the SCR is so high, that pretty much means that predictions will often be wrong by a relatively large amount. That part's not good. So there is light at the end of the tunnel with a low R squared. It just gives us more opportunity to find more contributing factors to our dependent variable. But with a significantly higher standard error of the regression, that means our predictions that we might extract from this are more wrong than right, unfortunately. Now, in order for our analysis that we've been performing to hold and to be reliable, certain assumptions must be true about the data. And what's notoriously difficult is testing some of these assumptions. We sometimes have to use qualitative evidence to suggest whether or not they're true or not, or we have to use anecdotal observations on why they might be false. And if these assumptions don't hold, we might have then enough motivation to try a slightly different model. So in the coming slides, what we're going to do is we're going to look at some of the least squares assumptions for causal inference. To what degree can we interpret the beta 1 coefficient as being the true impact of our deep independent variable on our dependent variable? Now, another way to say that in probabilistic type terminology is if our independent variable changes by 1 unit, so a unit change in x is going to have an impact on y. Okay, so for this to be the true causal impact of x on y, this beta 1 coefficient, it must be true that we must have random group assignments that are necessary. So thinking about an experiment, if you're thinking about the impact of a drug on weight loss or a shot, a vaccine on life-saving abilities, then what you really need is you need to have random assignment between these groups of treatment and the control, and you can test the average differences in life expectancy, let's say, or in weight loss to be the impact of the treatment on this parameter. So what we're going to do right now is we're going to make some assumptions about how X and Y are related to each other and how they are collected. That'll be particularly important. And so thinking about the sampling scheme in our data and across our natural experiment of observations. There are going to be 3 assumptions we'll talk about in turn. So with these 3 assumptions, we'll talk about the mathematical formula assumption, and then we'll talk about the interpretation as to what it means for our data. So for number 1, the conditional distribution of our error term, u, given x, has mean 0. This is something we can sort of look at when we are mapping our data in a scatter plot. And this says that regardless of what the level of our independent variable is, our error terms have a mean of 0. Okay, so they have kind of like a little central tendency towards 0. There are other confounding factors. Right, number 2, we say that our ordered pairs xi, yi, our observational data, is independently and identically distributed. Okay, so i.e. this is all random sampling, and we'll talk about the implications of that in the coming slides. And then number 3, that large outliers in x and or y are extremely rare. Okay, so there is the possibility of measurement error. There is the possibility of these rarely large values of our dependent and our independent variables, but they happen very infrequently. Okay, this is an important qualification for identifying the standard error of our estimated parameters. Now let's think about the assumption number 1 in the context of an example. Let's say we're thinking about an ideal randomized experiment. Again, who gets the drug, who gets the treatment? We are not thinking about outside characteristics that are individualistic to you. We're just saying we're going to blindly put people in 2 different groups. All right, so X, the treatment variable, would then be randomly assigned. Okay, so students to different size classes, regardless of your ability or your gender or your nationality or your intelligence. Or you can have that these variables, in another example, patients might be randomly assigned to treatments. Now, if it's true, by the allocation mechanism by which X is distributed to one variable or another, or one group to another, if it's actually randomly assigned, then any other individual characteristics, anything that makes up our error term, right, anything that's not strictly controlled for, these are going to be distributed independently of X. So U and X are independent variables. So going back to our example of both test score, our dependent variable, and the student-teacher ratio, we know that any other variable that impacts test scores that you are not controlling for, that's going to be bundled up into our error term. These are the other factors, quote unquote. So we were talking about this earlier. What are some other factors that might impact test score? Well, some classrooms might have better or newer books with more correct answers. There might be better teachers in one class for another. So you might be controlling for the number of students in the classroom. But if you have 30 students in a classroom with an amazing teacher and you have 10 students in a classroom with a poor teacher, you actually might have better test scores in the classroom with more students with a higher student-teacher ratio. We might also have, again, language barriers, immigration status. Those are other factors that we're not controlling for, potentially. So if it's true that our independent variable X is uncorrelated, right, uncorrelated and independent of our error term, all these other things we're not controlling for, then this expected value of equal to 0 is plausible. Okay, but if they are correlated, maybe because of some anecdotal information, then this least squared assumption number 1 is violated, and that means that our estimator for beta 1 is problematic. We'll talk about that in due turn. Now in least squares assumption number 2, this is when we're talking about our data that we're sampling. Our xi combination pairs are independent and identically distributed. This kind of happens automatically if we can somehow prove that we indeed do have random sampling. Right, so if the entity, if we're talking about individuals, or the districts, if we're talking about schooling, is sampled by random samples, observations. So if we're looking at test scores, let's say in the country, right, if let's say all 100 samples are from the contiguous United States or just the United States in general, then we can say that these entities, these classrooms, these districts are sampled from the same population, since it's the same country, which means they have identical distributions. But if you kind of compare that, if you have, let's say, 99 samples from the United States and you have 1 or 2 or 5 from a different country, those are quite different sampling distributions. Right? They're different populations. So you have to be very careful with what we're comparing and what we are claiming as far as our data actually tells us. It depends on where they're sampled from. Now, if these entities are selected at random, then technically these pairs of x's and y's, because they're different and they're selected at random, they are independently distributed. They don't have anything in common necessarily because they're random with other observations in the data sets. So you're going to see something a lot IID data It's usually something that we always assume to be true, but there are clear violations, and we'll see this in future chapters. Non-IID sampling is any time, let's say, for example, data is recorded over time with the same exact person. So when I look at your height over time, or your weight, let's say, over time, during the pandemic, before the pandemic, and after the pandemic, technically these observations are not independently distributed because your weight right now is very much tied to your weight tomorrow and your weight 10 days ago. So with this type of panel data or time series data, looking at individuals or countries, the same ones over time, we're going to slightly modify our model, and we'll see that in chapter 10 and beyond. All right, so the third and final assumption has to do with outliers. All right, so what to do about outliers? Are they truthful data? Are they measurement errors? Is it a coding error? We assume in the least squared assumption number 3, that outliers are extremely rare. Okay, an extremely rare value, and in fact, it could be a mistake quite frequently. So the main issue is if large outliers were relatively common, that would greatly influence, let's say, the slope that we fit to our regression line. Okay, it's going to greatly result these estimated parameters, and that's problematic. So we need to rule out large outliers and graph our data to see if there's any data point that we would have extracted or collected that may modify our results. Just one data point modifying our total model and influencing it is problematic. So what's the applied takeaway right here? Anytime you're estimating regressions, it might seem counterintuitive, but graph the data, right? Look at your data, generate a scatter plots, and if you have a large outlier, we have to really question, is this a typo? Did someone make a coding error? Is there a measurement error somewhere down the line? Does it belong in the actual data set? If it's an outlier and it was improperly coded, then we have permission from the make-believe econometric manipulative beings that we can remove this and feel okay with this removal. But if we look into it and it's not actually an outlier and it wasn't a measurement error, but it's actually a true data point, then we know that this data point is going to greatly influence our model, which we'll see in the next diagram. So let's say we have a collection of information. Let's say we have our independent variable x. Let's say we have our dependent variable y, and we're trying to estimate the true relationship between these two variables. Now the slope, because this is a one regressor model, the slope of this estimated line is the causal impact, potentially, of x on y. Right? So all of these little black data points right here are potential sample points, and then we have one up here. Okay? So down here, we have this blue line that's more flat. This is the OLS regression line that excludes that outlier up above. And what we see with this bottom regression line is that the slope, beta 1, is more or less equal to 0. It's a flat line for all intents and purposes. Okay? But if we look a little bit above, if we actually include that outlier up here, we see that it is such a large differentiation from the normal data down below that it's actually greatly individually influencing the slope of the regression line, which now beta 1 is strictly positive. All right, so if we exclude that outlier, this effectively says that the level of x does not actually have a calculated impact on y. If we exclude the outlier, this is beta 1 is effectively 0. But if we include that outlier, this is saying actually no, it has a slightly positive effect. I mean, that's a big difference, having no effect versus having a positive effect. So we have to really question, is this one low data point, is that outlier, is it an outlier that was because of measurement error, or is it, for all intents and purposes, a correct data point that is going to influence our estimated regression? We have to think long and hard. All right, so going back to our applied logic, in practice, outliers are often data glitches. Again, humans, we are prone to mistakes. We make coding errors. We record things incorrectly at some level of the data collection. And it's critical to plot your data and investigate. All right, so some quite shady econometricians might say this data point right here is messing up their model, and they might say that is an outlier. They're going to qualify it as an outlier, and they will delete it. if they don't like the results, including it. That is very questionable. A true scientist would investigate, is that data points the effect of mismeasurement of the variables, or is it an actual true data points? Okay, we have to investigate to decide whether or not to include it or not. Plotting and visualizing these data points helps a lot. Now, moving on from the assumptions of our OLS methodology, let's talk about the sampling distribution of this OLS estimator. Right, so the sampling distribution is asking, is trying to identify, in theory, what is our average expected estimator and what is the variance of this estimator? Because the reality is we estimate our slope beta 1, we estimate our intercept beta naught based off of a small subsample of the actual population. Okay, so because this OL estimator is computed with a sample data, then that means that technically different samples generate different estimates of beta 1. That is quite problematic. Right, so let's say there's 100 million, let's say, in the population. And let's say our small sample of estimating some type of coefficient, we take a sample, let's say sample 1, that's going to be equal to, let's say, 1 million. Sorry. And we get some estimate for beta 1, call that B1. Well, if you take a new sample, sample 2, with still 1 million observations, we're going to get a very different B1. Is it a stark difference in what B1 is estimated to be? Maybe, maybe not. We don't know. But the reality is every single time you collect a new sample, you will find a slightly modified, maybe potentially largely modified estimate of both B1 and B0. So then our task is to quantify the sampling uncertainty associated with actually estimating our beta 1 component. If we can identify the sampling distribution of our OLS estimator, we know what it is on average, and we know what it is in variance, then that will be very helpful for hypothesis tests and confidence intervals. So what do we need then? To identify the sampling distribution, we need both the mean and the variance of our sampling distribution for beta 1. Now, the derivations are in the chapter index, but again, in applied class, we're going to focus on what we can use quantitatively and qualitatively and avoid the derivations for now. Now, there are different sampling distributions depending on if we have small samples or large samples, but most serious analysis doesn't happen with small samples of, let's say, 10 or 20 observations, but more with 50 or more. So we're going to strictly focus on the large N approximation of the distribution of our estimated beta 1 coefficient. Right, so assuming the assumptions we talked about held and we have large N, then we say that beta 1 can be approximated using the normal distribution. Okay, so we have then that for large N, our betas are approximately distributed, again, because we are estimating but one of them, and every single time you resample and you estimate beta 1 again, it's going to be a different beta every single time. On average, we find that we have an unbiased estimator. The mean for beta 1 hat will be indeed the true population parameter, beta 1, and the variance, well, that's a little bit more complicated. We're going to have the variance of V, where V is equal to our xi minus the average of the x's times the error. Okay, so we're going to take the variance of that for all of our data points. A little headache to do in Excel. And then we're going to divide that by n over the squared variance of our x variables. All right, so we effectively have the mean and the variance of our estimator, beta 1 hats. And I don't know about you, but looking at that and calculating it by hand in Excel, you do it, it takes like 20 minutes and you get the correct answer and you feel really good about yourself, but then you realize you can plug that data into Stata, click a button, and it's there within 10 seconds, maybe even less. So yeah, we're not going to focus too much on the hand calculations of this, but more focus on what we can use it for down the line with the analysis. Now, taking a screenshot from the book, we have key concept 4.4 that will be used extensively in the next chapters, but will you ever actually come into contact with it, calculate things by hand? No. But what we have right here is the large sample normal distribution of our beta 1 coefficient. Okay, so this is our variance, which you just saw in the prior slide. And we also have a sampling distribution for our intercept as well. Because again, every single time we collect a new sample, we're going to get different estimates for our beta naught parameter. Right, so we're going to have this right here being the variance, and h right here is defined as this amount right here. Again, calculating this by hand is nothing that we want to do and not for the faint of heart. Thankfully, we have regression software that will output this information for us and help us utilize this for calculating both hypothesis tests and confidence intervals. So this right here, you're never going to have to deal with individually. You're instead going to be able to utilize this output from any type of regression software to talk about different analyses of the data. All right, let's go ahead and close up this chapter with looking at an empirical exercise from the end of chapter 4. This is empirical exercise number 4.1. So in this class, again, in lectures, in section, we will try to introduce you to as many problem-solving exercises, but also the empirical exercises that use Stata and other similar programming software. This comes from a data set that will be accessible to you. I linked this in the syllabus. The textbook has data sets for all of the empirical exercises on our website. Click on that website and you're going to download the data sets entitled growth. I believe it's an Excel file. And this data set has a lot. Right now, we're just going to focus on the dependent variable and one independent variable, but we're going to reintroduce this and revisit it later in the class when we start looking at multiple regression analysis and other types of analyses down the line. So here you'll see quite a few variables. We'll have average growth rates from 1960 to 1995 for 65 countries. All right. We're going to look at how those are related to growth in per capita GDP, in trade shares, in schooling, in revolutions. But right now, just with this chapter, since we're looking at just a simple linear regression, we want to identify the relationship between growth and trade. And here trade is identified as the exports plus the imports. Right? So all of that in and out of goods in a country divided by, as a percentage, the GDP in a country. This will be identified as the trade share in a country. All right, so let's go ahead and assume that you've downloaded the data sets from the publisher's website. Open Stata, and what you want to do is you want to type in the following into the command line, either in the command line or you want to open up a do file and save your command lines, which is what we try to do to save our work. But you're going to type the following command. It's going to be import Excel because this is an Excel file, and you're going to put quotes, and you're going to write users, and you're going to tell it the file path of where your data is actually located. So what I usually do is I download the data to a data file, and then I right-click the data file, and I look at the information for that file, and I copy the path, and I paste it right here. Actually, I paste it right here. It's this whole thing right here. So it'll give you users all the way down to the file. Then you put the file name. It's growth.xlsx because it's an Excel file. And then end that with a quotes, put a comma, and you're telling it that you want data to only extract the very sheet that's entitled growth. Because sometimes you have an Excel workbook that has multiple worksheets. So you're telling it to look at one particular sheet, and that's the growth worksheets. And in particular, right after that, you're going to type first row. You typing first row is you telling Stata that you actually have variable names in the first row. Don't include those in your scatter plots and use that for analysis. Label your variables accordingly so you can actually know what they're called. Okay, so you're telling Stata how the data is organized with a first row that's obviously names, not numbers. All right, so once we've done that, again, one of the first things you want to do is visualize what's going on between your variables. Now, graphs are great when you're looking at a simple linear regression where you have a dependent variable and an independent variable. If you start adding multiple independent variables, then you're not looking at a two-dimensional space, you're looking at an n-dimensional space. And it's hard to even mentally picture what that looks like. right? So looking at it in this two variable world where we have trade share on the horizontal axis and you have growth on the vertical axis, you can find this graph right here to visualize it by telling it to graph a two-way scatter plot, and you tell it the y variable and the x variable. Now visualizing this, do we think a relationship actually exists between these two variables? I mean, if you fit a line, would a line go up? Would it go down? Would it go up, then down, and oscillate all around? Well, I mean, I don't know how you would draw a line, but I would draw a line that kind of looks like this if I had to do my best to mimic the data that we've collected. So this scatter chart, this helps us visualize the relationship between the data. And I don't know about you, but I'm anticipating when we run a regression to probably find a beta 1 coefficient, the slope, that's going to be positive. Do we have any outliers? Maybe. Maybe the only outlier is, let's think about this. Outliers. Are there any outliers? Is there anything that varies significantly on the x-axis or the y-axis? The y-axis, not so much. This point on here, this throws me off a little bit. Most of our data is concentrated with a trade share between, let's say, 0.2 to, let's say, 1.2. So 0.2 to 1.2. And you have this number, right? You have this observation on here that's at 2. Something's happening there. But we will investigate in just a moment. All right, so having visualized the relationship in the scatter plots in the prior slide, now we can actually run a realistic regression to estimate the causal impact of trade share on growth. All right, so in part C, it says using all observations, run a regression on growth on trade share. So growth is our dependent variable. Trade share is our independent variable. What is the estimated slope? What is the estimated intercept? And then we'll use that information to predict the growth rate. So predict the growth rate when the country has a trade share of 0.5 versus when it has 1.0. All right, so having imported the data already into Stata, this now becomes relatively easy. We're going to tell it to regress growth on trade share, and then we're going to put comma R, so we have robust standard errors, which we'll talk about in the next chapter. And then it gives us output. We have all the Stata outputs. And again, like I said, it's important to get used to the Stata output, even if you decide to use a different statistical software like SPSS or R or MATLAB or something in between. Please get used to the Stata output, as exam questions will use Stata output, and you want to be able to know where to look for each particular part, right? So you can answer questions come exam time. Now we see right here from this output that the estimated intercept is going to be 0.64, and the estimated slope is 2.31. So if we have y hat is equal to b naught plus b1 times x, where x is going to be trade share, then if trade share is equal to 0.5, we can plug that in right there. We can plug in the estimate for b naught and b1, and we'll find that the estimated growth happens to be 2.95. All right, so we plugged in these numbers right here for both b naught and b1. And when you put the trade share being 1.0, then we find that the estimated growth is now 1.80. All right, so we've used estimated results about the regression and these parameters to predict the dependent variable under varying conditions of the independent variable. And here that's trade share. Now in part D, it says estimate the same exact regression, but excluding the data from Malta. So recall we had a lot of data. I'm not going to go back. A lot of data. And then we had 1 point over here. Okay, so a lot of points over here. And we had 1 point over here. And this is saying actually exclude Malta from our analysis. Now it turns out that Malta is this little island in the Mediterranean, kind of like off the boot of Italy. And it's what's considered a freight transport site. Right? So this is why it has such a large trade share. Where again, trade share, so trade share they define it to be exports plus imports divided by GDP. So theirs was 2.0, which was effectively much higher than this bounded amount that we saw with the other observational data. And it turns out this place in the Mediterranean, what they do is they import a lot of goods from the rest of the world and they turn around and they export it immediately. They're kind of like an intermediate site for global trade, or at least trade in the Mediterranean. So this suggests that unlike other countries that import goods and then export other goods, they are an intermediate step. They import and export so much more categorically, systematically than every other country. So they qualitatively are probably not a good data point to include in estimating the relationship between trade share and growth, since they are so different on an economic level and a procedural level than the other countries. So excluding Malta, which has a trade share equal to 2. I think it was equal to 2. What we can do is we can estimate the regression again and tell the regression to leave out certain data points. So what do? We regress growth on trade share, just like we did, but we're going to put a little qualifier. If the trade share is less than 1.5. Okay? So you can do this a few different ways. You can say if the trade share is not equal to 2, or you can say if it's less than 2 or less than 1.5, we'll get the same answer either way. Okay, sometimes it's nice to pinpoint and focus on a subset of our data to see if any of our analysis changes. Okay, so we can hopefully anticipate and explain why that happens. So when we exclude Malta, which has a large trade share, then we find that the trade share coefficient is no longer above 2. Now it's 1.68. And the constant that I think before was like 0.64 is now 0.95. So that outlier then significantly impacted our coefficients. And then when you plug in and we try to predict the growth, estimated growth for different trade share levels, we find that this estimated growth for trade share of 0.5 is 2.6. And then below, when the trade share is just 1, then the estimated growth is 1.8. So this did not change, but this right here is actually lower than our previous estimate. All right, so which one is the more likely impact? Which one is the better predicted growth based off of a trade share of 0.5? Probably the one that's comparing and utilizing countries that are more similar. This one right here is an outlier. This probably should be qualitatively and realistically excluded from the analysis. All right. All right, so we looked at an empirical exercise. We looked at some end of the chapter exercises. That concludes this review of Chapter 4. If you have any questions at all, please let us know in the discussion forums. Talk to us in office hours or in sections and let us know how we can help. All right, have a lovely day.